Now it's time to talk about the conservation of momentum. And to understand where it comes from and what it means physically, let's do a couple of experiments. Let's say we have two balls out in space, a red ball and a green ball. And initially, the red ball is moving at 1 meter per second, and the green ball is stationary. But once the red ball starts moving, we notice that after the collision, the red ball stops completely, and the green ball continues to move, still at a velocity of 1 meter per second. So we might think about this, and we might develop a law. We might say that it appears that in the case of a collision, if the initial velocity is v, the final velocity is the velocity of the red ball, final, plus the velocity of the green ball, final, and that's still going to be the same velocity v that we started with. So let's see if that checks out. So we find that we actually have another ball. We have a blue ball. And we decide to do this experiment. This time, we notice that the red ball bounces back in the opposite direction, whereas the blue ball continues on in the same direction. Only the red ball has a speed of 1/3 its initial speed, and the blue ball has a speed 2/3 the initial speed. So does our law hold? Well, it doesn't, because remember, velocity is a vector. But we say, let's try and modify this slightly, and we'll say the magnitude or the speed of the ball still be the same. So we look at the speed of the final velocity of the red ball and the speed of the magnitude of the final velocity of the blue ball, and we see that that's still v. So maybe that's what it is. Maybe speed is conserved in a collision. Well, we're in luck. We have one more ball. We have a yellow ball. So we decide to try this same experiment and see what happens. This time, we notice that the red ball continues traveling to the right, but at 1/3 of its initial velocity, and that the yellow ball is now moving at 4/3 the initial velocity of the red ball. So not only is velocity not conserved, but we actually seem to end up with more than we started with. Because now in this case, we have 1/3 the initial velocity plus 4/3 the initial velocity. So we have 5/3 the initial velocity of the red ball. So that's not what we wanted. But we notice that we also have a scale. And we can measure and find that the mass of the red ball is m. The mass of the green ball is also m. The mass of the blue ball is 2m, and the mass of the yellow ball is m/2. So now let's look back at those collisions, and let's define a quantity as the mass times the velocity of the red ball. So initially, the red ball has mass m and velocity v. The final velocity in the case of the green ball, the mass of the red ball is still m, but its velocity is 0. The mass of the green ball is m. Its velocity is v. So m times v seems to be conserved. Well, let's look at the blue ball. So in this case, we have mv before the collision. The mass of the red ball is still m, But if you remember, it was moving in the negative direction with a third its initial velocity. The blue ball was moving to the right at 2/3 the velocity. So now we have 4/3 minus 1/3 mv is still equal to mv. So once again, m times v is conserved. So let's try our last case. So in our last case, we have again the same initial mass times velocity. Now the red ball is moving to the right with a velocity of a third its initial velocity. The yellow ball is moving at 4/3 the velocity with half the mass, which tells us that 2/3, so 1/3 plus 2/3 mv is once again mv. So we notice that in all three cases, this quantity, m times v, the mass times the velocity, was conserved. And we call that P as a symbol, and that's the momentum. So something's momentum is its mass times its velocity, and we notice that momentum is a vector, right? This wouldn't have been true if we looked at the speed because of this negative sign when this particle is moving to the left. So it's very important that we remember that momentum, like velocity, is also a vector.